All right, shall we get started? From this giant nightmare. Okay. So what I want to say is that this is a flow chart representing all the organic compounds and all of their reactions on how we get from one to another. Memorize isn't the right word, but it's kind of the best way to describe it. You kind of need to know all the reactions that are going on and how we get from point A to point B. The reason why is I'll show you guys some of the exam questions. These are the ones I'm going to hand out later today. First off, you're going to need to know how to do these conversions because they're going to give you these flow charts, and you have to identify, what things go in here and also what reagents you need to do that conversion. So that's one reason why you're going to need this. The second reason why you're going to need this is you're going to get questions like this that are going to ask you to convert from one organic molecule to another. So they want you to convert from propan-on, which is our ketone, to ethylpropanoate, which is an ester. So they're like, how do you do that? The way you do that is through these conversion reactions. Okay? So let me walk you guys through it and the different types of reactions that occur. There is going to be a color code at the bottom, and I'll also make some notes on here as well. I've made yours bigger than mine in case you guys want to add any extra notes and things like that. And I'll show you what I mean when we start actually writing. All right. The first type of reaction that we're going to go through is addition reactions because I think that they're probably the easiest to understand. Yes, I'm going to go through addition first, I think. All right. So I'm going to highlight the addition reactions in orange. This marker doesn't work. I'm throwing it out. So the orange ones are, we're looking for alkene, and we're going from alkene to something else. So this one's going to be orange. And this one's going to be orange. And this marker doesn't work there. So the orange is showing my addition reactions. My goodness, so many dud markers. It's like 3 in a row now. There we go. All right. So I'm color coding these guys as orange. All right. These are what we call addition reactions. And I think we have talked about them briefly before. So when we are talking about addition reactions, we are starting with an alkene, and you are adding to it. So basically what we see with these addition reactions is that I have my C double bond C, and then I add something to it, and then I break my double bond to then form my single bonds, like that. So that's what we call it, addition. Are we okay with that so far? Yes, no? Okay. So if I'm looking back at my flow chart over here, here's my alkene C double bond C. I could break my double bond and add a haloalkane to it, or sorry, add a halogen to it to make it a haloalkane. Or I could go and break the molecule and make it into an alcohol. Do you guys want me to annotate what those functional groups look like? So a haloalkane would be a carbon with some sort of halogen attached to it, CX. Alcohol would be C with an OH. So several different ways I could do this. When it comes from the alkene to the alcohol, if I want to go in that direction, what I would need is to heat it with diluted sulfuric acid. So I would go H2SO4 with heat. And this needs to be dilute. We don't need it to be very concentrated. So what you'll see with a lot of the marking schedules is that they will expect you to specify if it's concentrated or dilute, if you need heat. So this detail here with the dilute and the heat, that's going to be stuff they're going to be looking for an excellence level answer. So if I took my alkene and I heated it with sulfuric acid, I would be able to make an alcohol. Are we okay with that so far? Right. If I want to go to alkene to a haloalkane, there's several different options to it. First way I can do is by, I'm just trying to find it. There it is. I could just add the halogen that has, what is it? A halide? I think that's what the word I was looking for. So it has the hydrogen and X is representing any of the halogens. So I can add that to my alkene and that would get it to convert. The other option is I could use like bromine or chlorine. I do have to remember if I do those things, we are making a di version of it. So either dibromo or dichloro. Are we okay with me saying that? Yes, no? Yep. Keep in mind when we're looking at these sort of addition reactions, we need to potentially factor in Markovnikov's rule. So that is the rich getting richer. So when we're looking at the carbon involved in the double bond, whichever has the most hydrogen is most likely to gain another hydrogen. So that's why I gave you guys some extra space so that way you can make some notes on there like that. So if you're thinking about these addition reactions, you might need to think about Markovnikov's rule. Markovnikov's, I need to figure out how to spell that now. And there we go. Is like a potential thing that you might need to think about. Markovnikov's rule. If you're not sure what to do with Markovnikov's rule, there are some pages in the SciPad you can do, and I have noted them on Google Classroom, I believe. Right, we okay with that so far? Markovnikov's. Zoom in if you guys want. Markovnikov's. He's the guy that made up the rule, or discovered the rule, I should say. So it just means that when you have an asymmetrical alkene, the two components, say for example, the OH and the hydrogen could be added in one direction or the other. Do you want me to show you an example? Yeah. So for Markovnikov's rule, so let's say I have an alkene like this. And I want to add water to it. So this is going to be an example of an addition reaction. And you'll need dilute H2SO4 and heat for that reaction to occur. So when I break this double bond, I have two potential products. So what I could have as my first potential product, when I break this up, I'm adding an H and I'm adding an OH to it. So I could add the H onto carbon number 1, and thus the OH goes to carbon number 2, or I could have the OH go to carbon number 1 and the H go to carbon number 2. There are two potential products there. Markovnikov's rule states that the one with the most hydrogens, this is carbon number 1 with 1, 2, versus carbon number 2, which only has one hydrogen, the one with the most number of hydrogens is more likely to gain another hydrogen. Sorry, those H's look really bad. So since this one had the most number of hydrogens, it gains the hydrogen. So this is what we call the major product. The minor then is in the instance that the hydrogen doesn't go on the rich carbon. So both products can occur. Just as a side note, if I have a carbon molecule, say the double bonds here, if I have a carbon molecule, this is my double bond, that's right here. Both of these carbons only have one hydrogen. They'll still be two products, it's just they're going to be in a 50-50 ratio. Just no major, minor. It'll just be a 50-50 ratio. Are we okay with that? So that's what happens with Markovnikov's rule. So those are addition reactions. So there's only two of them. All right, can I go back to the flowchart? Matthew, you ready? So next thing on the flowchart, let me try to actually highlight this. Oh God, I hate the sound of like the dry highlighter and scrapes the paper. I just need one of you to work. Okay. Ooh. Okay. So those are my addition reactions. The next one I'm going to do is the elimination because they go hand in hand. There we go, one that works. All right, elimination. So elimination is also tied to the alkene. In this case, we are going from something to the alkene, so the arrow's in a different direction. That's why I have it in a different color. So elimination reactions are when we remove something from our molecule. So we remove two groups, I'm going to call it atoms, whichever, to form an alkene. So basically, we have a molecule, say, for example, our alcohol. Just going to draw it out big so you can see everybody. Actually, I'll put another C there so we can look at Zeta's rule. So I have an alcohol here. And what we're going to do is we're going to remove two things. So let's say I take away the OH and a hydrogen. And then what I'm going to be forming is a double bond. So we eliminate to form our double bond. So that's our elimination reaction. So a lot of these reaction names correlate to what is going on. So two elimination reactions that we're thinking about. The first one we have is going from alcohol to alkene. In this case, for me to do that, I would need concentrated sulfuric acid. So conc H2SO4, and again, I would need heat. So again, we can see both of these are requiring sulfuric acid, but one of them is concentrated, one of them is dilute. So we do need to keep track of this information. Concentrated. The other thing I have is haloalkane going to alkene. If I wanted to do that, I would need, say something like potassium hydroxide in alcohol. So I'm going to write. So again, those specific conditions are really important, and you'll see why when we start looking at some of the other reactions. Are we okay with that so far? All right. Figured I'd start with those because those ones are probably the easiest. All right. Now, when we go in this direction to the alkene, we have a similar situation known as Zaytev's rule. So I'll write that in yellow that you might need to use. And that is spelled Zaytev's rule is basically like Markovnikov's rule, but going in reverse. So we call this one the poor gets poorer. Saytzeff. Zaytev's. You might also see this spelled with a Z at the front. So when we're looking at Zaytev's rule, what we're thinking about, and again, there's some SciPad pages if you need more time on it, is that the carbon with the least amount of hydrogen are more likely to lose the second hydrogen. So basically, if I was doing an elimination and I wanted to remove the OH, I need to take off a hydrogen from one of the neighboring carbons. So I could either take it off carbon number 1 or carbon number 3. Carbon number 3 has 2 hydrogens. Carbon number 1 has 3 hydrogens. So it's more likely that I'm going to lose a hydrogen off of carbon 3. So again, we have 2 products. We have CH3, CH, double bond, CH, CH3 as one product. And then our second product has the double bond instead, forming on carbon 1 and 2. So again, you have the major minor situation. This one will be the major. This one will be the minor. Because the double bond can form either between carbon 1 and 2 or 2 and 3. So just pointing it out because sometimes on these flowcharts they do have major minor products. The flowchart that I have for you guys here doesn't, but I think when you convert from propane on to ethyl propanoate, you might need to select one of the two. Are we okay with that? All right. Can I switch it? Yeah, Mime, we're ready? Okay. The next set of reactions are, it's quite a bit of a long list. These are our substitution reactions. Nope, I'm going to color code that in green. They occur in lots of different areas. So I will first give you guys the definition of substitution. Substitution is just like the word substitute, like you have a substitute teacher, or you go to a restaurant and you ask them, hey, do you mind if you substitute mashed potatoes for French fries? It's just a swapping of our function groups. Substitution is just swapping. So in the ones that we were talking about, we were adding and removing. In this case, we are just swapping one thing from another. So looking at this flow chart, there's lots of different spaces that this could happen. Haloalkane to alcohol, you can swap out the X and the OH. So these two are both substitution reactions in both directions, going from one to another. We also have a substitution going on if we want to take off the haloalkane and make an amine. And I've separated out the secondary amines from the primary amines. Sorry, secondary and tertiary from the primary. So those are both substitution reactions. Just as a reminder, with amines, we're talking about a carbon attached to a nitrogen. That's a primary. A secondary would have the nitrogen having 2 carbons attached to it. And then a tertiary would have 3 carbons attached to it. But basically what you're looking at doing is you're swapping out the halogen for an amine group. So that's another location that you'll see it. These two, you're swapping the OH and the halogen. And then the other place you will see it is down at the bottom with our carboxylic acid kind of grouping. So you'll see the carboxylic acid, which is our C double bond O OH. That OH can get swapped for other things. So if I swap out that OH and I go and add a Cl, then I get my acid chloride. If I go in the other direction, then I get my alcohol back. So the acid chloride is that C double bond O, Cl. So those two is what's getting swapped around in that case. We could also have things substituted out for my carboxylic acid or my acid chloride for an amide. So that one's also a substitution reaction. So again, you're changing up that guy. Let's see, esters to amides. And we could also get our esters to amides swapped out. So an ester could become an amide. So lots of locations for substitutions. They're more common because you're not then tied specifically to an alkene. Again, we do need to know what we need for our different reactions in the reagents. So let's go through and add that. So if I want to go from haloalkane to an alcohol, just trying to see, I would need KOH. In this case, I would need it to be aqueous, so I just want it in water. So you see I have KOH in 2 instances. One is being dissolved in alcohol, the other one being dissolved in water. That's really important which one you're using because it will change where you're going pathway-wise. If I want to go from an alcohol to a haloalkane, I would need SOCl2. Haloalkanes are real central and alcohols are real central. So when you're trying to convert from one thing to another, you're probably going to have to use that as an intermediate step. If I wanted to go from haloalkane to primary amine, I would need, I think, just ammonia. With heat. If I want to go from haloalkane to secondary alkane, for the secondary, I would need to have a primary amine. And for the tertiary, I would need to have a secondary amine. Basically, all you're doing is adding a carbon to it. It's very unlikely you're going to be asked about this corner, but I wanted to show it to you in case. That's what you need in that corners. Most of them kind of make sense to what they're being added. So like with the alcohol, in order for me to get rid of the OH, I would and put it in a chlorine, I need that reagent. All right, keep going. Go look at the bottom. All right, if I wanted to go from a carboxylic acid to an acid chloride, you need the same reagent as you do from alcohol to haloalkane. Oopsie, putting in the wrong spot. And if I want to go from a acid chloride back to a carboxylic acid, I would just need water, which we talked about already in the identification test, because if you add water, it reacts quite violently, forming then the carboxylic acid. If I want to go acid chloride, where are you, acid chloride? To an amine, I would need just trying to find it. So carboxylic acid to amine, you would need ammonia. Again, in this case, it needs to be in water. If I wanted to go from an acid chloride to an amide, I would need it in alcohol, which makes sense because if I had this in water, it would react to form a carboxylic acid. And also, it would neutralize it. And then if I want to go from an ester to an amide, I would need the ammonia again in alcohol. So those are all my conversions over there. And that's why I gave you guys the flashcards. So that way, hopefully, it made it a little bit easier to memorize all these reactions. Questions, concerns, comments, or keep going? Yeah. Haloalkane is secondary amine. You would need to have a primary amine because you're attaching another carbon to it. Do you want me to show you what that looks like? Okay. So if I had a haloalkane, like C, let's say I had this, and if I want to make a secondary amine, I would have something like something like that. So that's already a secondary amine, or sorry, a primary amine, because it has a nitrogen that's only attached to one carbon. What would happen when I was doing the substitution reaction is one of the hydrogens would leave and the chlorine would leave to form a bond. So I'd have CH3, CH2, N, because it's attaching there, H, CH3. So that's how that two molecules would combine together, making a secondary. Yeah. And then if I wanted to make a tertiary, I would need a secondary like this to be added. But it's very unlikely they'll ask you that question. But that's what's basically happening. And if I wanted to make a primary amine, then I would just have the halogen and I would add ammonia. So the ammonia would replace the halogen. Cool. Keep going. I know it's a lot to take in. That's why I want to show you the full flow chart. Cool. So next thing that I would add is my oxidation reactions. So I'm going to do that in pink. Oxidation. And you guys should know the oxidation reactions because we've talked about it as identification tests. So if I want to go from an alcohol to an aldehyde, that's an oxidation reaction. Yeah, the stationary pack has the pink. Sorry. So we've already talked about this. If I have a primary alcohol and I oxidize it, I would get an aldehyde. And if I oxidize that aldehyde again, I would get a carboxylic acid. So those are both oxidation steps. If I had a secondary alcohol, it would oxidize to a ketone. So this is the pathway for a primary alcohol. This is the pathway for a secondary alcohol. And you have a lot of choices when it comes to your oxidation reactions. You can use any oxidant. You could use dichromate, which is the Cr2O7 2-. Needs to be acidified for that to work. You could also use permanganate as well. So both of those would oxidize it. So these are just your oxidation reactions. Primary and secondary alcohols. So primary alcohol, if I oxidize it, I form an aldehyde. So that would be your C double bond O on an N carbon. Whereas the ketone is the double bonded oxygen that's not on a center carbon. And then this could be further oxidized to a carboxylic acid. And again, I've given you guys extra space if you want to make some extra notes. So like, for example, you might want to make notes on the identification test as well, being like, I could tell an aldehyde from like using Tollens or Fellings or Benedict's. So if you want, you could write extra notes to help you summarize what's going on. So those are oxidations. Oh, I want the purple for the reductions. All right, and like we were talking about in redox, there's oxidation and reduction, so I can reverse this reaction by doing a reduction. So I'm highlighting that guy in purple. So reduction are going to be these two reactions. So basically I can go backwards if I need to, which is important when you guys are trying to do your conversions. There we go. So that's reduction. In order for me to do that, I will need NaB4. I'm just checking to see if there's any other things that they've written down. Four, and then lithium is the other option. This one I think might be the stronger oxidant. So that's just the reagent. So we can reverse things if we need to. Just watching the time. I don't want to talk too long. I've already been talking for 30 minutes. All right, ready for the last one? Not yet. This is just one color left. Sure. All right, last one I have is condensation reactions. I have two versions of it. One that you will need a catalyst for, and one of them you don't need a catalyst for. And that just has to do with the fact of whether or not you're using the acid chloride or not. So all the remaining ones are examples of condensation reactions. Just trying to quickly color it. And what you'll notice with the condensation reactions is that we're taking two things and we're adding them together. So I'll put that as another note. Condensation is taking two organic molecules together and removing water to make a larger molecule. Hey. Yeah. All right, so two organic molecules being added together by removing water to make a larger molecule. So for example, the one that I have shown you guys is, and we've talked about this before with the esters. To make an ester, we take a carboxylic acid and an alcohol to do that. So like for example, alcohol plus carboxylic acid equals ester. Should do an arrow. Because when you think about the ester functional group, you had C double bond O, O, and then you had two like R chains from it. And if you remember, I said one of these R chains is from the carboxylic acid, and the other R chain is from the alcohol. So two molecules have been added together. Another one that you guys can get is, I'm just going to move it, is the amides. So if you think about an amide, I should say secondary, tertiary, which again shouldn't come up, but it might. You could have an amide that is like that, where this has come from a carboxylic acid, or an acid chloride is the other possibility. And that's coming from an amine, and that makes your secondary or tertiary amide. But those are very unlikely to come up on the exam. Just in case it does, because I do see it happen every so often. Just want to point it out to you guys. So if we were looking at our flow chart, can I move it? Or are you guys still writing? Looks like you guys are still writing. All right, can I move it? Move it? Okay. So like, for example, if I was going to go alcohol with my carboxylic acid, these two guys coming together, to form my ester, I would need to have, where are you? Carboxylic acid, ester, alcohol. There we go. Concentrated sulfuric acid and heat, if I was to do that. In the case of using an acid chloride, because the acid chlorides are more reactive, so you can see the acid chloride here and the alcohol coming from up here, we would just need to mix them together and they would react. No further reagents that we need. And then we do have acid chlorides combining with amines. We could do that as well as my other addition, or as my other condensation reactions. And all of these would remove water. But it's unlikely they'll ask you one of those. If we were doing something like that, you would need, in the case of the primary and the acid chloride forming the secondary, you would need those two mixed together. Or you take the secondary and you mix it with the acid chloride and you get a tertiary. In both of those cases, you'll just mix them. And that's the whole flow chart. Nice and big for you guys so that way you can put it on as like a poster. Okay, I'm done teaching so I can go and help. All right, I'm going to pass out 2 questions for you guys to do and use this flow chart to help you. I think this one's probably the easier of the 2 because it's scaffolding because it's scaffolded and you can kind of see what's going on. In this case, you are starting with an ester and you're breaking it apart. I could do that if I had sulfuric acid. So figuring out how I break my ester into 2 bits and then looking at how you go down the different kind of steps to get this guy at the end. This question here is a little bit trickier. You're trying to figure out how to go from a ketone to an ester. So you're going to have to do a couple of backward steps and then forward. So I'll pass this out, give it a go. I'll do some clarifications for it at the end. All right, I'll just show you guys the answer for the one that you're working on. So you guys are all working on the flow chart. So this here is your ester. If we heat it with diluted sulfuric acid, we would break up our ester. We'll talk about the hydrolysis of esters and amides in a later lesson, so don't stress. You get your carboxylic acid and you get your alcohol. Going down the carboxylic acid chain, you can go from a carboxylic acid to an acid chloride by using SOCl2. And then if you had concentrated ammonia, you can then swap the chlorine for the NH2. And then if I wanted to go from ammonia, amide back to carboxylic acid, I would need sulfuric acid and just heat. Oh, sorry, I forgot that one on the flow chart. So that's how you go backwards. If you want to add that as a note, we should add that as a note. If I want to go backwards from a primary amide back to a carboxylic acid, you want SO4. Sorry, sulfuric acid, dilute, and heat. All right. The other side was the easier side because you're going from primary alcohol to a aldehyde and then aldehyde to carboxylic acid. Now, here's the thing. Those things are tricky, but my goodness, they are so easy to get points if you know what you're doing. Any 3 answers that are correct on that table would be enough for an achieved. 5 correct answers, one of which needs to be a reagent. There were, how many questions on there? 1, 2, 3, 4, 5, 6, 7, 8. You just need 5 out of 8, one of them being a reagent to get a merit point on that. And then excellence is getting all of them. So it's tricky in a sense that you need to know how the flow chart works, but if you know how the flow chart works, it's a very easy excellence point. And this is why I'm saying over and over and over again, organic is easier to get the excellence on, so long as you know what you're doing. So you need to know that flow chart. All right. The other question you guys had was the conversion question, which is a little bit trickier because you have to work forward and backwards, and it's not scaffolded for you like the flow chart. But they do ask both versions on the exam. All right. Questions, concerns, comments? No? All right. Yeah, that's it then. These are the recommended work to follow up on. I will give you lots of time to work on these conversion and flowchart questions because I'm mindful it takes a while to kind of wrap your head around. Just keep in mind that for this week, we did organic today. Thursday's lesson is going to be organic and thermo together because the skill set I need to teach you works in both categories. And then Friday, I'll just let it be a study day for organic. I think study day for thermo. Organic, I will give you guys a flow chart for your question. But we'll still work on this material next week. So you got a little time.